Now we know that the musicians who play string instruments like the guitar, like the violin, like the cello, they need to tune those strings because they relax with time and their sound will be out of phase or not following the frequency that they should be following. Otherwise, you would hear that this music is not sounding that good. So tuning a stringed instrument involves several principles of physics. We use heavily the universal wave equation, which means the velocity equals frequency by the wavelength, and indicates that the frequency of sound wave is directly proportional to the speed of the sound and inversely proportional to the wavelength. The wavelength for the fundamental frequency of the standing wave in a string is fixed at twice the length of the string, but the speed of a wave in a string increases with tension. So if the wavelength does not change, the frequency at which the string vibrates must increase with tension. Changing the tension in the string is known as tuning. We know as well wind instruments produce different musical notes by changing the length of the air column. So we can see here, if we go to the lab and we have a closed pipe, then we see that the resonance would occur and the node must be present at the closed end while the antinode is created at the open end. If the pipe is open at both ends, then the wavelength for which the resonance occurs must have antinodes at both ends of the open pipe or the open tube. The distance from one antinode to the next is 1/2 the wavelength, which means the longest wavelength that can resonate in an open pipe is twice as long as the pipe. So the length of a wind instrument is important in producing the right notes and the right sound. So we can see here in a closed pipe, the longest possible resonant wavelength is 4 times the length of the pipe, L equal 1/4 by lambda. And for the open pipe, the longest possible resonant wavelength is twice the length of the pipe. So L equals lambda over 2. Let's assume the frequency of a source is 100 Hz and the speed of sound is 350 meters per second. According to the universal wave equation, if this source is at rest, the wavelength of the sound is 3.5 meters. So using the universal wave equation, V equal frequency by lambda. In this case, lambda would equal V over frequency. V is 350 as given, and frequency would be 100 Hertz or 100 per second. That would give you 3.5 meters. So when a wavelength of 3.5 meters travel towards you at a speed of 350 meters per second, you would hear a sound that has a frequency of 100 Hertz. Now there is a concept we need to explain called the Doppler effect. So if you hear a sound at a frequency of 100 Hertz, the speed is 350, and the time lapse between the humps, the positive humps, is 3.5 meters apart. That would be 1/100 of a second. If the wavelength that traveled toward you were 7 meters long, the time lapse between successive positive humps of the wave would be 1/50 Hertz, and the frequency would equal 250 Hertz. That is coming from the universal wave law, which means frequency equals V over lambda. V is 350 over 7, that will give you 50 Hertz. Now, things a little different when you have a moving object or a moving source that is producing a sound. In this case, the way you hear that sound is different. That can be imagined when you are standing beside the highway and a car passed by. You will hear that kind of closing by effect. Then, like, you feel the sound is giving you that sporty sound we always represent when we want to explain a car that's going in a speed in a vocal way. So why you don't hear the sound of the car in a constant way? Why it just kind of squeeze and give you that kind of weird sound for the engine of that car? We explain that through the Doppler effect. Imagine that the source is generating 100 Hz sound. 100 Hz, the sound is moving towards you at a speed of 70 meters per second. Assume the source in this case at point A when it generates the hump of the positive wave, while the first hump moves a distance of 3.5 meters towards you, the source also moves towards you. The distance the source moves while it generates one wavelength is the distance the source travels in 1 over 100 hertz at 70 meters per second or 0.7 meters. Now, because of the motion of the source, the next positive hump of the wave is generated at point B, and it will be only 2.8 meters behind the first hump, as long as the source continues at the speed of 70 meters per second towards you. Now, the positive hump is traveling in your direction will be only 2.8 meters apart. So for a car moving towards you, the sound waves emitted by the car will be kind of squeezed together, and it will reach you more frequently than if the car were stationary. So if the waves that are at 2.8 meter long travel towards you at a speed of 350, then the frequency of the sound arriving at your ear will be 125 hertz. The pitch of the sound that you hear will have been increased because the source is moving towards you. So it's kind of when the car is on the highway moving towards you, it is not giving the sound enough time to reach you, and all these waves of sound will combine together and squeeze in a short period of time. So it's kind of you heard the sound of the engine accelerated, like as if you put a video on like 2 times the speed or 3 times the speed for a few milliseconds. That's why you hear that squeezed sound when the car passed by you. If you want to explain that mathematically, you have the universal wave equation, V equals frequency by lambda, frequency equals V over lambda. 350 over 2.8 would give you 125 hertz. At the same time, along a line in the direction opposite to the motion of the source, the wavelengths are increased by the same amount that the wave in front of the source are shortened. 400 Hz sound source moving at 70 meters per second, the wave behind the source are increased by 0.7 meters to a length of 4.2 meters. The time lapse between these crests or positive humps of the signal, which are 4.2 meters apart, traveling 350 meters per second, is 0.012 seconds. So the perceived frequency in the direction opposite to the motion of the source is 83 Hz. The pitch of the sound would be lowered. So again, the analysis of the Doppler effect, if the velocity of the sound wave in air is Vw, then the wavelength is lambda s, that is a stationary source with a frequency of frequency s, would give you lambda s equals Vw over Fs. To analyze the Doppler effect, you need to calculate the distance of the source that the source moved in the time required to generate one wavelength. The period Ts of the source is used in this case. If the source is moving at a speed Vs, then in the period Ts, the source moves a distance delta ds. That would be represented as Ts equals 1 over Fs. Delta ds would equal Vs over Fs. When the source is moving towards you, delta ds is the distance by which the wavelengths are shortened. Subtract delta ds from lambda s would give you the length of the waves lambda d. That is the length of the wave that reached the listener. So therefore, lambda d equals lambda s minus delta ds. Replacing lambda s and delta ds by their equivalent forms given, that would give you lambda d equals Vw over Fs, that's for the lambda s, minus delta ds we know equals Vs over Fs from here. So lambda d would equal Vw, or the wave speed in air, minus Vs, the wave speed stationary, over the frequency of the stationary. So this is the apparent wavelength, or what's called Doppler wavelength, of the sound generated by the source that's moving towards you at a speed of Vs. Dividing the speed of the wave Vw by Doppler wavelength lambda d will produce the Doppler frequency Fd of that sound that you hear as the source approaches toward you. So the frequency of d would equal Vw over lambda d, and you replace lambda d with the variables found earlier. That would give you FD equals VW over VW minus VS multiplied by frequency of S, or frequency stationary. Now, when the source is moving away from you, the value of delta ds is added to the value of lambda s, would give you lambda d equals lambda s plus delta ds. You replace lambda s and delta ds by their equivalent forms and complete the development to find fd. You can see that the Doppler frequency for a sound where the source moves away from the listener is given by fd equals VW over VW plus Vs by frequency S. So the general form of the Doppler equation can be represented or written as a single equation in the form of Fd equals Vw over Vw plus or minus Vs multiplied by frequency of S. Taking an example on the Doppler effect, we have a train traveling at a speed 30 meters per second. Its whistle generates a sound wave with a frequency 224 Hz. You're standing beside the track as the train passes you with its whistle blowing. What is the change in frequency do you detect for the pitch of the whistle as the train passes if the speed of sound in air is 330 meters per second? So we have Fs, stationary frequency 224. We have the VW, that's the speed of sound in the air, 330 meters per second. And we have Vs, need to find Doppler frequency for the whistle as the train approach. We use the equation for Doppler shifts to find Doppler frequency of the whistle for approaching whistle and for receding whistle. So we say Fd equals Vw over Vw minus Vs by frequency S. And that would give you, by replacing all those givens, as 330 over 300 by 224 would give you 246 Hertz. So the frequency for the approaching whistle would be using this equation and give you this result. And the frequency using the receding whistle would be using the plus sign here for this equation. And you replace all the givens and would give you 205 Hertz. Now let's find the change in frequency, or the change in pitch in this case. That would be difference in the two frequencies. So the pitch change will be delta frequency would equal 246 Hertz minus 205 Hertz would give you 41 Hertz.